Hello and welcome back. Today we will have lecture 8-3, a supplemental lecture on filter design. The objective is to design filter circuits to meet design requirements. It is sometimes more convenient and simplifies the mathematics to design passive and active filter circuits with element values such as 1 ohm, 1 farad, and 1 henry. Scaling can then be used to transform the circuit in values for R, L, and C to more realistic values. There are two types of scaling, magnitude and frequency. In magnitude scaling, the scale factor multiplies all of the impedances at a given frequency. In frequency scaling, the scale factor multiplies each impedance such that it is the same as it was at the original frequency. Note that the prime terms are the scaled values and the unprimed terms are the original values. The following table summarizes how you scale resistors, inductors, and capacitors. When it's magnitude scaling, the scale factor is Km, and a prime resistor is Kmr, a prime inductor is Kml, and a prime capacitor is C over Km. In frequency scaling, the scale factor is Kf. A primed resistor is the same as the original resistor. There is no frequency scaling because resistance is not dependent on frequency. A primed inductor is L over Kf, and a primed capacitor is C over Kf. To simultaneously scale magnitude and frequency, we use the following equations. R prime equals Kmr, L prime equals Kml over Kf, and C prime equals C over Km Kf. Example 1. Design a high-pass active filter with a high frequency gain of 5 and a corner frequency of 2 kHz. Use a 0.1 microfarad capacitor in your design. For the following circuit, the transfer function H of S is equal to negative Ks over S plus omega C. This is the general form for a high-pass filter. Using the components on this circuit, that becomes negative R2 over R1 times S over S plus 1 over R1C, which is going to equal, for our design specifications, negative 5S over S plus 2 pi 2000. So K is equal to R2 over R1, which equals 5, and omega C is equal to 2 pi 2000, which equals 12,566, which equals 1 over R1C. Remember that C is equal to 0.1 microfarads per the design specifications, so R1 is equal to 1 over 12,566 times 0.1 micro, which equals 800 ohms. And since K is equal to 5, R2 is going to equal 5R1. So R2 is equal to 4,000 ohms. The gain in decibels, or the magnitude of H of j omega in decibels, is equal to 20 log base 10 of 5 omega over the square root of omega squared plus 2 pi 2000 squared. The loss in decibels is equal to 10 log base 10 of omega squared plus the quantity 2 pi 2000 squared over 25 omega squared. Example 2. The following Butterworth low-pass filter is designed such that the cutoff frequency omega C is 1 radian per second. Scale the circuit for a cutoff frequency of 50 kilohertz using 10 kilo ohm resistors. The top circuit here shows the prototype for a fourth order Butterworth filter. And the circuit at the bottom shows the answer after we've scaled it, and we will demonstrate how to get these values. How do we know that this is a fourth order circuit? Well, the circuit has 2 inductors and 2 capacitors, which is 4 energy storage elements. Remember, the order of a circuit is based upon the number of energy storage elements it has. It could be 4 capacitors, it could be 4 inductors, or in this case, 2 inductors and 2 capacitors. How do we know it's a low-pass filter? Well, you look at the magnitude of h of j omega as the frequency goes to 0 and as it goes to infinity. As it goes to 0, we get 1/2. Remember, frequency of 0 is DC conditions. Under DC conditions, an inductor looks like a short circuit and a capacitor looks like an open circuit. So when I redraw the circuit under DC conditions, I see that I'm down to the 2 resistors and the source, and if I measure the output across the 1 ohm resistor, then that's going to be a gain of 1/2 using the voltage divider. So now I look at the frequency response as the frequency goes to infinity, and as omega goes to infinity, an inductor looks like an open circuit, and a capacitor looks like a short circuit. And so when I draw this, I see that although the output is measured across the 1 ohm resistor, I have an open circuit, so that output's going to be 0. Thus, I have a low-pass filter. So for the prototype, omega C is equal to 1 radian per second. And the scaled frequency based upon the design specification is 2 pi 50,000 radians per second. So Kf is going to equal omega C prime over omega C, which equals 2 pi 50,000. So R is equal to 1 ohm for the prototype, and the scaled R, or R prime, is equal to 10 kilo ohms. So Km is equal to R prime over R, which equals 10,000. And now we're ready to scale all of our prototype components using the scale factors Kf and Km. The fourth order Butterworth has a transfer function h of s equal to 1/2, because the gain k is 1/2, over s squared plus 0.765s plus 1 times s squared plus 1.848s plus 1, which means that if I found the transfer function for that prototype circuit, this is what it would be. We label on the circuit L1, L2, C1, and C2. And now we're looking for L1 prime, L2 prime, C1 prime, and C2 prime. L1 prime is equal to Km over Kf L1, which equals 10 over 2 pi 50 times 1.848, which equals 58.82 millihenry. L2 prime is equal to Km over Kf L2, which equals 10 over 2 pi 50 times 0.765, which equals 24.35 millihenry. C1 prime is equal to C1 over Km Kf, which equals 0.765 over 10K times 2 pi 50K, which equals 243.5 picofarads, and C2 prime equals C2 over Km Kf, which equals 1.848 over 10K times 2 pi 50K, which equals 588.2 picofarads. Theory. A prototype low-pass operational amplifier filter has R equal 1 ohm, C equal 1 farad, and a cutoff frequency of 1 radian per second. In order to create a sharper transition from the passband to the stopband, it is necessary to cascade filters. The more filters that are cascaded, the slope of the transition increases by 20 decibels per decade. Each additional stage increases the order of the transfer function for the filter. The higher order cascaded prototype low-pass filter has the following transfer function. H of S is equal to -1 to the n over S plus 1 to the n, where the cutoff frequency is the square root of the nth root of 2 minus 1. As more stages are added to a filter, the cutoff frequency changes. The resultant filter can be frequency scaled in order to adjust it to the desired cutoff frequency. Kf is equal to omega c over omega cn. Since the gain of the higher order filter is not 1, an inverting amplifier can be cascaded with the resulting filter to adjust the gain. An alternate method for designing a higher order filter involves the use of Butterworth filters. Note that most of the Butterworth filters are a product of first and second order filters. The first order transfer function can be produced using a low pass op-amp filter, and the following table provides the circuits for the second order transfer functions for the low pass and high pass Butterworth filters. So this table has a second order Butterworth low pass filter that has 2 resistors and 2 capacitors, and the general formulas are B1 is equal to 2 over RC1, and R squared C1 C2 is equal to 1, and the transfer function is 1 over R squared C1 C2 over S squared plus 2 over RC1S plus 1 over R squared C1 C2. If you scale this prototype so that omega c is 1 radian per second, R is equal to 1 ohm, and K, the gain, is equal to 1, B1 is equal to 2 over C1, C1 C2 is equal to 1, and the transfer function is 1 over S squared plus B1S plus 1, which equals 1 over C1 C2 over S squared plus 2 over C1S plus 1 over C1 C2. The second order Butterworth high pass filter also has 2 capacitors and 2 resistors. So the general formulas are B1 is equal to 2 over R2C, R1 R2 C squared equals 1, and the transfer function is S squared over S squared plus 2 over R2CS plus 1 over R1 R2 C squared. If we assume omega c is 1 radian per second, C is 1 farad, and the gain K is equal to 1, B1 is equal to 2 over R2, R1 R2 is equal to 1, and the transfer function is S squared over S squared plus B1S plus 1, which equals S squared over S squared plus 2 over R2S plus 1 over R1 R2. The following figure illustrates another method used to describe a higher order filter based upon the four variables AP, AS, omega P, and omega S, so that you can determine the order of the filter based upon the passband, the stopband, frequency, and gain, where AS is equal to the magnitude of h of j omega s in decibels, or 20 log 10 of 1 over the square root of 1 plus omega s to the 2n, which equals negative 10 log base 10, 1 plus omega s to the 2n. And here's a plot of what these values look like for the low pass filter, where you have the pass band, the transition band, and the stop band, with the values for the gain AP and AS and omega P and omega S delineated. If we assume that omega P is the cutoff frequency, then the order of the Butterworth filter is N is equal to negative 0.05 AS over log base 10 of omega S over omega C for a low pass filter, or N is equal to negative 0.05 AS over log base 10 of omega C over omega S for a high pass filter. Advantages of the Butterworth filter versus the Cascaded filter. As the order of the Butterworth filter increases, the cutoff frequency remains the same. A lower order Butterworth filter achieves the same design specifications as a higher order Cascaded filter. It takes less operational amplifiers to implement a Butterworth filter with the same order as the Cascaded filter. The following figure shows a Butterworth and a Cascaded filter with the same order, and notice that the Butterworth has a steeper cutoff, although it would be designed with less op amps. Example 3. Design a third order low pass Butterworth filter with a gain of 1, cutoff frequency of 2 kHz, and 1 kilo ohm resistors. The prototype for a third order Butterworth filter is a first order low pass filter cascaded with a second order low pass filter. So here is the first order prototype with a 1 ohm resistor, a 1 farad capacitor, and a 1 ohm resistor in the feedback. And then here is the second order prototype with 2 resistors and 2 capacitors. All the resistors will be 1 ohm, but now the capacitors will be C1 and C2, where their values will be determined in order to create the Butterworth polynomial. K is equal to 1. Omega C is equal to 1 radian per second. And the transfer function h of s for the Butterworth polynomial is 1 over s plus 1 times 1 over s squared plus s plus 1, which equals 1 over s plus 1 over RC times 1 over s squared plus 2 over C1s plus 1 over C1 C2. So for n equals 1, the first op amp, we're going to have R is equal to 1, C is equal to 1 farad, and for n equals 2, the second op amp, for the prototype case, we're going to have 2 over C1 is equal to 1. So C1 is equal to 2 farads. And 1 over C1, C2 is equal to 1. So C2 is equal to half a farad. So now we can put these on our prototype. C1 is 1 farad and C2 is half a farad. So now we scale the prototype. R prime is equal to 1 kilo ohm. So Km is equal to R prime over R, which equals 1,000. Omega C prime is equal to 2 pi 2,000. So Kf is equal to omega C prime over omega C, which equals 2 pi 2,000. So C prime is equal to C over Km Kf, which equals 1 over 1,000 times 2 pi 2,000, which equals 79.6 nanofarads. C1 prime is equal to C1 over Km Kf, which equals 2 over 1,000 times 2 pi 2,000, which equals 159 nanofarads. And C2 prime is equal to C2 over Km Kf, which equals 1/2 over 1,000 times 2 pi 2,000, which equals 39.8 nanofarads. And finally, this is what the prototype scaled third order low pass Butterworth filter would look like with a gain of 1, a cutoff frequency of 2 kilohertz, and 1 kilo ohm resistors. Example 4, design a fourth order high pass Butterworth filter with a gain of 1, cutoff frequency of 2 kilohertz, and 10 nanofarad capacitors. The prototype for this filter will be 2 second order high pass filters cascaded together. So since both circuits are second order, they both will have the capacitors on the input to the positive terminal, and one feedback resistor and one resistor that goes to ground. We will label all the capacitors 1 farad, and on the first circuit the resistors are R1A and R2A, and on the second circuit the resistors are R1B and R2B. H of S for the fourth order Butterworth polynomial is equal to s to the fourth power over s squared plus 0.768s plus 1 times s squared plus 1.848s plus 1 which equals s to the fourth power over s squared plus 2 over R1A S plus 1 over R1A, R2A times S squared plus 2 over R2B plus 1 over R1B, R2B. Note that in that first polynomial, the middle coefficient should be 2 over R2A, not 2 over R1A. So now for the prototype values, when K is equal to 1 and omega C is equal to 1 radian per second, in the first op amp we will have C is equal to 1 farad, 2 over R2A is equal to 0.765. So R2A is equal to 2.614 ohms. And 1 over R1A times R2A is equal to 1. So R1A is equal to 0.3825 ohms. For the second op amp, C is equal to 1 farad. So 2 over R2P is equal to 1.848, and R2B is equal to 1.082 ohms, and 1 over R1B, R2B is equal to 1, so R1B is equal to 0.924 ohms. So now for the scale factors. Kf is equal to omega C prime over omega C, which equals 2 pi 2000. Km is equal to C over Kf C prime, and remember C prime is 10 nanofarads. So Km is equal to 1 over 2 pi 2000 times 10 nano, which is equal to 7,958. So now to scale the components. C prime is 10 nanofarads. R1A prime is Km R1A, which is 7,958 times 0.3825, which equals 3 kiloohms. R2A prime is equal to Km R2A, which equals 7,958 times 0.614, which is equal to 20.8 kiloohms. R1B prime is Km times R1B, which is equal to 7,958 times 6.924, which is equal to 7.35 kiloohms. And R2B prime is equal to Km R2B, which equals 7,958 times 1.082, which is equal to 8.61 kiloohms. And finally, let's see what the final scaled circuit looks like that meets our design specifications of a 10 nanofarad capacitor and a cutoff frequency of 2 pi 2000 radians per second. And this concludes today's lecture on filter design. Have a great day.